This conference will now be recorded.
Okay. All right. So let us start with the session. So in the previous class, we were discussing things with respect to the digital keypad. We actually started with the programming of a digital keypad. First, we programmed a single key, which is switch 1. And what we did was, with respect to the switch 1, we took action throughout the switch being pressed. So that was level detection. And whenever the switch is being pressed for once, we also took the action which was state detection. So throughout the switch being pressed, as long as you keep the switch pressed, if you keep taking the action for multiple times, that is level detection. If you press the switch for once and you want to take the action for only once, that is state detection. So you either can read the switch with respect to the state detection or edge detection. Both of them are the same. So state detection, or you can read it with respect to the level detection. So we first started with the program of one particular switch. Okay. Uh, and how to create our own header file. Okay. So I think I have not showed you that. So let me first take that and then proceed. Okay. So I was telling that we have configured one particular switch, and we read it for state as well as level. After that, we also did one more program to write the driver of the digital keypad. So we identified which key is being pressed. So whether it is the state or the level, we had to identify out of the 6 keys available which key is being pressed. So we also did that in the previous class. We wrote the driver. So today we are going to continue, but before that I have to show you how to add the header file. So let me directly take you to that particular topic. So I will open a first project what we did. Okay. So I'm going to close this project and open the project which we first did regarding the LED. So going to the files, and when I do the open project, okay. So I'm going to the, okay, give me a second. Let this project get closed first. Okay. So I'm going to file and I'm going to open the project. So I'm opening the project which we have previously done with respect to the LED. For that, I'm going to show you how to add the header. So I took led.h head project. Now, first, whenever you have to add the header file, you have to go to the header files. Okay. So this is where you're going to have all of your header files stored. So I'm going to do a right click and you have to click on new. Okay. So first you have to go to header files. Okay. And I have to click on new. Now I will be given with multiple options. So you can directly click on see header file. Okay. So if you want, you can directly click on see header file if there is an option. If there is no option, then you can go to others. Okay. Then click on see, and then you will get the option called see header file. Okay. So you can just go to header files, right click, new, see header file, or go to others, then see, and in that you have to select see header file. So if you click on next, it asks you the file name of the header. So I'm going to give it as main. Okay. Then the extension, keep it as H because I'm trying to create is a header file. Once you're done giving the name and giving the extension, you have to click on finish. That is going to create a header file by the name main. So you can see this is main.h header file. Now once the main.h header file has been created, you can delete all of these contents except the first 2 lines and the last line. Okay. So delete everything except the first 2 lines and the last 1 line. Okay. So everything, this has to be deleted. So you just retain the first 2 lines and the last 1 line. Now, being inside this, whatever you want to write to your header file, you can write. So actually, whatever macros I wrote here, let me have it written in the header file. That is easy for proper maintenance. So I'm going to have it written here. So LED array port D, LED array's data direction register is TRISD. Also, this headers inclusion, I will write it in my header file itself. Okay, so I'm going to write the headers inclusion also in the header file itself. Now I have written xc.h and two macros in my header file. Now this header file should be added to your main.c file. Okay, so that user defined header file should be added to your main.c file. How to include a user defined header file? What should I use to include a user defined header file? /include preprocessor directive you use. Apart from that, yes, I should write it in double quotes. The moment you type a single double quotes, it gives you the option. So whichever header file is available in your project. So I have main.h. So I'm going to click on that. So main.h is going to get included. So if I include main.h in my main.c file, that is literally including your xc.h header and the two macros which you have written in your header file, the main header file. Okay, so that is how you are going to include a user defined header file, or that is how you are going to create your own header file. You can go to header file, you can click right click, you can select the option new, and then you can go with C header file. Okay, so after this you follow the normal steps to build, execute and see the output. Is that clear? Okay, ma'am, what is a driver? Okay, so if you are asking about the driver code which I have been talking so far, so I have been telling that what we wrote is a driver code. Okay, so with respect to the digital keypad, what we wrote was a driver code. So driver code means you don't have to like write the configurations from the begin again and again. So it is like a code which will help me access the hardware easily. So that is a driver code. So for any hardware, you will have a driver associated to it. To establish the communication with the hardware, you need a driver for it. So for this also, especially for your any peripherals you write, we will write its own configuration kind of a program. For example, if you see the digital keypad, we wrote it for the initialization. We also wrote a function for performing the operation with respect to the digital keypad. So that we call it as a driver code. So code which is associated to a specific peripheral in general is nothing but a driver code. Okay, fine. All right, so I hope your people are clear with this. So let us proceed with the next topic for today. So in today's topic, initially to start with, I will take one of a configuration of the digital keypad. So I will take one switch connected to the microcontroller as that of our board. Okay, so as you see on our board, so I will see one set of only one switch, in fact, connected to our microcontroller. So assume this is the switch I am drawing. So one end of the switch has been connected to the microcontroller and another end of the switch has been connected to the ground. And in order to help with the pull up, okay, so I'm going to have a resistor which is pulling the line up whenever the circuit is being open, and I'm having it further connected to VDD. Okay, so this is the resistor, and here I'm going to take a switch. So please assume this as a notch. Okay, and this assume is the RB0 pin of your microcontroller. So this is the microcontroller. Okay, now one end, as I said, is being connected to the ground, another end is connected to the microcontroller pin, which is RB0. So this I will say VCC or VDD, whichever you are comfortable with. And this is how the circuit is being connected on board. How a single switch is being connected to the microcontroller on board. Do you agree with this? Do you agree that this is how the circuit has been available on board? Guys, are you people there? Okay. Now I will write a small program. Just keep an eye on the program. So I'm taking a main function. Okay. Now being in the main function, assume I'll be inside while of 1. Okay. So I'm inside while of 1. Now being in the while of 1, so assume I want to perform some operations. The first set of operation, I will not write what the code is. I will just write it as a comment and assume I have a code which is consuming approximately 100 milliseconds for its execution. Okay, so there is a code which is approximately consuming 100 milliseconds for its execution. Then, how are you going to check if the switch has been pressed or not? So what should I write here in the condition? How to check if the switch is pressed or not? Can you help me what to write? Yes. So I should write RB0 is equal to 0. So there is a switch connected to the RB0 pin of the microcontroller. If that RB0 falls down to 0, then the switch will be pressed. Now whenever a switch is pressed, assume I'm supposed to take some action. Okay, so I'm least bothered with what action it is. I will just write it as a statement. So I'm supposed to take some action. Okay, then after this, assume there is one more code which is approximately taking around 1000 milliseconds for its execution. So code of 1000 milliseconds. So I'm writing a simple code. First I'm inside void main while of 1. So inside while of 1, I'm writing a code which is consuming approximately 100 milliseconds. Then I'm checking if RB0 is equal to 0. I'm supposed to take the action. Then I'm also writing a code which is consuming approximately 1000 milliseconds of time. Is there any doubt in this code? Are you able to understand this code? Okay. So it's a very simple code. Now first and the foremost thing, let us draw how the hardware is going to respond whenever a switch is pressed. Okay. So I'm writing a hardware response for how a switch is being pressed. Okay. So assume instead of this RB0 pin, there is a switch which is connected to the CRO. Okay, so there is a switch which is connected to the CRO. So it is something like this. I'm talking about the hardware response now. How hardware is going to respond. So first and the foremost thing, I'm having the response drawn here. So I'm drawing voltage versus time graph. So on the x-axis I take is time, and on the y-axis I take is voltage. Okay, so this is let's say time. Okay, and this one is voltage. Okay, this one is voltage. So I will have two responses. Either the voltage will be 0 or the voltage will be 5 volts. So assume VDD is 5 volts. So either the voltage will be 5 volts or it will be 0 volts. Okay, now please answer. Whenever a switch is not pressed, okay, so assume the switch is not pressed. So what am I going to read at the CRO right now? So one end of the switch is connected to ground, another end of the switch is connected to the CRO. If switch is not pressed, yes, I'm going to read a 5 volts in the CRO. So I'm going to draw a line like this. Okay. Now, after some point of time, let's say at time X. Okay. So after some point of time, that is time X, I am going to press the switch. Okay. So at time X, I have pressed the switch. Now tell me, in the hardware, when I press the switch, will I be able to see if the switch is pressed or not immediately? Will I be able to see if the switch is pressed or not immediately in the hardware? So assume you are given with a switch. Okay, assume you are given with a switch. You press the switch. Will you not be able to identify switch is pressed or released? Look at this hardware itself. Okay, so I'll show you with respect to the Pixim lab board. Now see, look at this switch which I have got. Looking at the switch, will you not be able to identify if the switch is pressed or not? You can identify, right? And immediately when the switch is pressed, you can see in the hardware it gets identified. Yes or no? Immediately in the hardware, the moment switch is pressed, it gets identified. So the same thing happens here. So at the time X, if you press the switch, immediately the signal falls down to 0. Do you agree? So do you agree? Immediately you should be able to identify the switch. So that is what happens in the hardware. The moment you press the switch, immediately the switch press will be identified at the time X itself. So you are going to see a 0 here. Now let us see a software response. How the software of our system is going to respond for the switch press. So I'm going to draw the software response for our switch press. So the software what I have written is the program, what you see here on the left hand side. So now we have to see how our software is going to respond for the switch I'm going to press. So response. Okay. So here the spelling is wrong. Please ignore. So I'm going to draw a graph for the software response also. The same voltage versus the time graph. Okay. So on the y-axis, you see the voltage. On the x-axis, you see the time. Now, in the software response, for the simple program which I have taken here on the left-hand side, I will end up getting 3 different scenarios. Okay. So I'll end up getting 3 different scenarios. Now let us see which and all are the scenarios. Now first of all, it's scenario number 1. Okay, so what I'm taking right now is scenario number 1. So what happens in scenario number 1 is, first and the foremost thing, let us start how that is going to work. So assume initially the switch is not pressed. What are you going to read at the pin of the microcontroller? That is RB0. If the switch is not pressed, yes, you are going to see a 1 at the pin of the microcontroller. So I'm drawing a 1 here. So assume this is digital 1 and digital 0 I'm drawing. So I'm going to read a 1 here. Now at the time X, okay, so user is pressing the switch. Okay. At the time X, user is pressing the switch. But your software has just started executing the code which is consuming approximately 100 milliseconds. Okay. Please understand, your user has pressed the switch in the hardware. Okay. That switch has to be identified in the software to take some action. So you have written a software to identify the switch press. Okay, this is the software you have written. So when the program has been running, at the time X, user has pressed the switch. Okay, but your software has just started executing the code of 100 milliseconds. Now, do you think your software will be able to identify the switch press immediately? Do you think your software will be able to identify the switch press immediately? No. In order to identify the switch press, your control has to come to this place. Yes or no? In order to identify if the switch is pressed or not, my control has to come to this place. Now, in order to come to the second line, how much time do you think the software takes? In order to come to the second line, yes, it takes 100 milliseconds in order to come to the second line. That means in order to identify if there is a switch press being made, it is possible only after 100 milliseconds, right? It is only possible. So if I press the switch at time X, I will be able to identify only after time X plus 100. Noise, guys, please take care of your mic. Okay, I will repeat it again. So if the user presses the switch X, and if user presses the switch at the time X, and your software is busy executing a code of 100 milliseconds, can I say your software will be able to identify the switch press only after 100 milliseconds? Yes or no? Yes. So your software will be able to identify the switch press only after 100 milliseconds. So I press the switch at time X, but I am able to identify it only at the time X plus 100 milliseconds. So here it is X plus 100 milliseconds. Okay. So that is scenario number 1. Did you get? Did you understand the scenario number 1? Okay. Now, there's a doubt. Okay, but after 100 milliseconds, if the switch is pressed only, then RB0 will become 0, right? Yes, Shreya. So what you're saying is right. So after 100 milliseconds, even if the switch is pressed only, you will be able to identify the switch being pressed. But I'll talk to that scenario a little late. Let me finish this right now. So I'm just telling what are the possible scenarios. In what scenarios you can have the switch press identified. So if I press the switch at the time X, I will be able to identify the switch press only after 100 milliseconds. So there is a delay of 100 milliseconds. Okay. Now coming to scenario number 2. So this is scenario number 2 I'm taking. Okay. And okay. So this is for scenario number 2. And this scenario number 2, I consider it as the luckiest scenario. Okay. Or I would say the best scenario. What is the press duration of the switch? So I haven't taken any such kind of an example, Chaitanya. So I haven't considered for how long the switch is being pressed. I'm just telling you that if the switch is pressed at the time X, you will be able to identify the switch press only after 100 milliseconds according to the code I have written. Okay, and there is a reason for me taking this topic. Please wait. Okay. All right. So coming to scenario number 2 here. Okay. So initially, I haven't pressed any switch. Okay. So switch is not pressed yet. So I will be reading a 1 at the pin of the microcontroller. Now at the time X, okay. So user has pressed the switch. Okay. This is time X at which user has pressed the switch. Now, luckily, your software was just about to check if the switch is pressed or not. So, it has just entered the statement. Your software has just entered the statement to check if there is a switch pressed or not. At the same time, you have pressed the switch in the hardware. Now, tell me, will your software be able to identify the switch press immediately? Will your software be able to identify the switch press immediately? Yes. So that is possible. So my software will be able to identify the switch press immediately. So this is called as the best case scenario. I press the switch and I could get it identified immediately. So that is the best case scenario. Okay. And scenario number 3 is like the worst case scenario. So I'll write it up here. This is scenario number 3. And this one is in fact the worst case scenario. Okay. Now what happens in this case is, so initially you have not pressed any switch. So your software should be reading a 1 at the pin of the microcontroller. So at the time X, okay, this is the time X. So at the time X, I am going to press the switch. But assume your software has just started to execute the code of 1000 milliseconds. After how much time your software will be able to identify the switch press? After how much time your software will be able to identify the switch press? Yes, it's 1100, because first it has to finish the execution of the code, which takes 1000 milliseconds. Then it has to finish the execution of the code, which takes 100 milliseconds. Only then it can be able to identify if there is a switch press being made. So your software will be able to identify the switch press only after 1100 milliseconds. Okay, so I'm going to drag this a little more. And this is for 1100 milliseconds. Okay, so I will be able to identify the switch press only after 1100 milliseconds. So this is X plus 1100. Now see, this is the hardware response I have got with respect to the hardware. Okay. And I want my software also to behave same as that of the hardware. So whenever I am going to press the switch, I should be able to identify the switch press being made. I press the switch at the time X, and if you see the software response, okay, just to identify one switch, I have got 3 different scenarios. So in the first scenario, I will only be able to identify after 100 milliseconds of delay. In the second scenario, I could identify it immediately. In the third scenario, I'm able to identify only after 1100 milliseconds of time. Okay. So understand, this is the hardware response I actually wanted in case of the software also. So I wanted the response to be same as that of the hardware, but I'm getting 3 different responses. Now tell me, whatever response I have got with respect to the software is a good response or a bad response? So whatever response I have got in my software is a good response or a bad response? So it is obviously a bad response. It is not good. So I was expecting something very similar to that of a hardware response, but I'm getting 3 different possible scenarios. So whatever I am seeing right now is in fact a bad response. Okay. So I can literally say that it is a bad response. Now please understand, I in fact started today's topic without even giving the name of the topic. So what we are discussing today is nothing but polling. Okay, so what we are discussing today is nothing but polling. Now what polling says is, if you see here, I have returned a statement if RB0 is equal to 0. So I have returned a statement. And this statement is something which needs to be constantly monitored. Okay. So I have to, in order to know if the switch is pressed or not, I have to come look at the RB0 pin again and again. I have to constantly monitor an event which is happening at RB0 pin of the microcontroller. Do you agree? In order to know whether I have pressed the switch or not, I have to constantly monitor this. I have to constantly keep an eye on the RB0 pin. I have to come to this particular statement again and again and check if RB0 is representing the value 0. So that is technically referred as polling. So if I have to write a statement with respect to the polling, okay, so polling is nothing but monitoring something or monitoring an event on a continuous manner. Okay, so that is nothing but polling. Monitoring an event on a continuous manner is nothing but polling. So that is what we have been doing so far. We have been keeping an eye on the RB0 pin of the microcontroller on a continuous manner. I'm keeping monitoring the RB0 pin, which is why we technically call it as polling. And what we are listing here is nothing but the drawbacks of polling. Okay, so whatever I have started listing, I wrote bad response, so that is nothing but the drawbacks of polling. Okay, so drawbacks of polling. So please understand, the first drawback of polling is bad response time. So you are constantly keeping an eye on the RB0 pin of the microcontroller. So definition of polling is monitoring an event on a continuous manner. So if you see, I'm constantly monitoring the RB0 pin of your microcontroller. I'm coming and checking again and again if RB0 is falling down to 0, just to see if the switch is pressed or not. So monitoring something on a continuous manner is nothing but polling. I'm monitoring the RB0 pin here, so that is called as polling. And what we have been doing is, we have been continuously keeping an eye on the RB0 pin. So due to this continuously monitoring the RB0 pin, I have come across the first drawback, which is nothing but bad response time. Okay, so I would say bad response time, in fact. So it is not responding properly to all of the inputs I am providing immediately. So that is the first drawback of polling. Now speaking about the second drawback of polling, observe this. Assume your software is somewhere here. Okay, so your software is busy executing a code of 1000 milliseconds. At that point of time, you have pressed the switch. Okay, at that point of time, you have pressed the switch. And assume you press the switch for 500 milliseconds only. Okay, you have pressed the switch for 500 milliseconds. After how much of time will you be able to identify the switch press in this scenario? No, like, do not consider the time for which I have pressed the switch. Generally speaking, if the software has started a code of 1000 milliseconds to execute, after how much time will I be able to identify the switch press? It is only after 1100 milliseconds. But I press the switch for 500 milliseconds only. Now, by the time I come here to check if the switch is pressed or not, do you think your software will be able to identify the switch press? By the time I come here, will it be able to identify? Obviously, no. In that case, did I not miss an event? Did I not miss an event in that case? Yes. So that is the second drawback of polling, that is loss of event. So there are chances of you losing the event. So that is loss of event being the second drawback of polling. Okay. So the first drawback of polling is nothing but the bad response time. The second drawback of polling is loss of event. There are chances of you losing the event also. Now, you didn't understand the loss of event. Okay, repeating again. So assume your software has started executing a code of 1000 milliseconds. Okay, so your software has started executing a code of 1000 milliseconds. After how much of time will I be able to identify the switch press? I have to finish the code of 1000 milliseconds. I have to finish the code of 100 milliseconds. Then I should come here and check if there is a switch press being made. Okay. Now assume your software has just started to execute a code of 1000 milliseconds, but you have pressed the switch for only approximately 500 milliseconds. Okay. You have kept the switch pressed for 500 milliseconds only. Now, you are able to identify the switch press only at this point. So you have to come here and check. Now, by the time you come here, 1100 milliseconds are over. At this point of time, if you see there is a switch pressed or not, will you be able to identify the switch press? I kept the switch pressed for 500 milliseconds only. By the time you came here, it is 1100 milliseconds. So meanwhile, I must have also left my switch. I have not kept it pressed. I have released my switch. So by the time I come here and see if the switch is pressed or not, obviously I will see that the switch is not pressed. Okay. So that is why I'm going to lose an event. So there is a loss of event also. Okay. So that is the second drawback. I hope you got this. Okay. Now speaking about the third drawback, okay, or in fact the last drawback. Assume you are continuously monitoring the RB0 pin of your microcontroller. So here, so again and again, because I'm inside while of 1, again and again you keep checking the RB0 pin of the microcontroller. Okay. So I'm continuously monitoring the RB0 pin of the microcontroller. Okay. So I'm continuously checking if RB0 has fallen down to 0. Now observe, I'm again and again have to come and check if RB0 has fallen down to 0. Because of this, do you think I can put my microcontroller to the sleep mode? So because I have to check if RB0 has fallen down to 0 or not, do you think I can put my microcontroller to the sleep mode? No. So because your microcontroller is the one which is monitoring whether RB0 has fallen down to 0 or not. So it is not possible to put the microcontroller to the sleep mode because I have to monitor RB0 pin on a continuous manner. Now, if I cannot put the microcontroller to the sleep mode, do you think I can manage the power efficiently? If the microcontroller cannot be put to the sleep mode, is it possible to manage the power efficiently? No again. So the third drawback of polling is inefficient power management. Okay, that is inefficient power management. Okay, so these are the three drawbacks of polling. So polling means monitoring an event on a continuous manner. So I'm monitoring RB0 pin here on a continuous manner. So because of this, what happens is, first and the foremost thing, you are getting a bad response time. So you're not going to get the response as that what you get in the hardware. Second one is there are chances of you losing some of the events because some other code must have been running and you will be missing out some of the events. And the third one is inefficient power management because you cannot put your microcontroller to the sleep mode. We have to keep 1100 milliseconds sleep mode. No, that is not possible. See, whatever the code is, your microcontroller has to keep an eye on the RB0 pin. It has to again keep checking. So for example, assume you are in the room, your mother keeps checking whether you stay in the room or not. Okay. So in that case, every time if your mom knocks the door and check if you are in, do you think you will be able to sleep? No, right? So something similar to that. Your microcontroller is again and again going and checking if RB0 is falling down to 0 or not. It is continuously monitoring the RB0 pin of the microcontroller. Now, because your microcontroller is busy monitoring the RB0 pin, please understand that your microcontroller cannot be put to the sleep mode. If your microcontroller is sleeping, it will not be able to check if RB0 has fallen down to 0 or not. Okay, so you cannot put your microcontroller to the sleep mode, and because you cannot put your microcontroller to the sleep mode, I will not be able to manage power on an efficient manner. So in the inactive times, I cannot put my microcontroller to the sleep mode. So the inefficient power management is another drawback of polling. So polling means monitoring something on a continuous manner. And the three drawbacks of polling are bad response time, the loss of event, and inefficient power management. Is that clear? Okay. All right. Then how do you think I can overcome the drawbacks of polling? What can I be doing in order to overcome the drawback of polling? Any idea? How do you think I can overcome the drawbacks of polling? Yes. So we have something called as interrupts. Okay. So instead of you monitoring something on a continuous manner. So for example, see, whenever I press the switch, I have to take the action. That is the aim of my software. So I have returned this application in such a way that whenever I press the switch connected to the RB0, I have to take the action. Rest of all other actions shouldn't be affected, and I should overcome the drawbacks of polling. So the only way of overcoming the drawbacks of polling is with the help of interrupts. So interrupts are going to help us overcome the drawbacks of polling. Now let us start with the next topic of the chapter, or next peripheral of the chapter to be discussing about, which is nothing but interrupts. Okay. So interrupts are the one which are used to overcome the drawbacks of polling. Now, what do you mean by interrupts in general? So I'm not asking with respect to any specific microcontroller or any specific programming language. I'm generally asking, what do you mean by interrupts? Okay. So yes. So interrupt means, okay, I can read some of the answers here. Disturbance, okay, fine. So interrupts, disturbance, something coming in between. Stop the process for a particular time, okay. Forcefully pause, something that comes in the middle of a task, okay. To stop current execution and concentrate on the occurred event, okay. Delay or stop. Polling will be in switches only or other peripherals as well. So it can be in other peripherals also. So if you keep an eye on something on a constant basis, like if you keep checking an event, that we refer as polling. So as of now, I can show it with an example of switch. So I have taken that example. It can be according to any logic you have written. Okay, so to stop an event in the middle of execution, fine, disturbing something or someone. Why do we still have polling if interrupts are better? So we don't have polling, but in some of the cases, interrupts are not helpful. So interrupts can be done for only certain scenarios. You cannot raise the interrupt for each and everything. Certain things have to be done with the polling method itself. It is unavoidable in certain scenarios. You'll see going ahead. So interrupts cannot be raised for every scenario. There are certain things which has to be monitored on a continuous manner. So, but you have to know what's the difference between polling and interrupt. Okay, all right. So yes, what and all answers I have got with respect to the interrupts are all right. So interrupts are nothing but something which causes a disturbance to the actual flow. Okay, so that is in short nothing but the interrupts. And if you technically speak about the interrupts, so it is just a signal. Okay, interrupt in fact is a signal which is given to your microcontroller or microprocessor to take care of some other task instead of something which is actually being done. Okay, so it's just a signal given to the microcontroller or a microprocessor in order to take care of some other tasks. Okay, so that is nothing but interruption. All right. Now, in case of this topic interrupts, we have got four things to be discussing in total. First one is the basic concepts of interrupts. Second one is the sources of interrupt. Third one is the classification of interrupt. And fourth one is how can a interrupt be handled. So these are the four things we are going to understand in today's topic with respect to the interrupt. So to start with, we will go with the basic concepts of interrupt. As I said, interrupt is nothing but a communication process, or I would say a communication signal, which is being set on a microprocessor or a microcontroller. Okay, so interrupt is nothing but a signal or a process which is done either in a microcontroller or a microprocessor. So what this interrupt does is it is actually a request which is either done by an internal device or by an external device. So interrupt can either be done by an internal device or it can be done by an external device, which is going to request the microprocessing unit to stop the processing of the current task. Okay, so it is like a request which will be raised by either the internal device or the external device for the processing unit in order to stop processing the task, whatever it has been doing. So after receiving the task, what microprocessing unit has to do is it has to acknowledge the request. Okay, whatever request it is receiving, it has to acknowledge the request. It has to attend that request. So it has to take care of that request and it has to go back to processing where it was interrupted. So something like assume we are in a classroom. So assume we are in a classroom. So I am the microprocessing unit, just assume, and I'm going to conduct the class. So I'm taking the class. Now let's say there is something important for me to be done. So assume somebody knocks the door of our classroom and asks me for some help. So what I will do is I will pause taking the class for some amount of time. I'll go attend the request of whatever I was asked for. Then I will come back and continue to take the class again. So that is nothing but interrupt. So interrupt can either be internal device or external device. So in the sense, if I'm taking the class, interrupt can be from someone among you, or it can be somebody who is coming from another classroom or from outside our classroom. So it can be something like that. So interrupt is nothing but so I'm not literally saying your doubts are interrupts. So I'm saying something which uh, obviously interrupts don't consider it as a disturbance. Okay. So consider it as an event which is unavoidable. So if I see any doubts, I cannot avoid it. I obviously have to address the doubt. Okay. So interrupt, yes, you instead of you considering it as a disturbance, you can consider something which is given with the highest priority. Okay. So something like that. So interrupt is nothing but a communication process or a signal which is given to the microprocessor or the microcontroller. Okay. There is no personal things involved. Okay. So don't consider things that way. I was just generally giving you an example. Okay. So don't think that the doubts are interrupts. And obviously, if you want to think it as an interrupt, please think that they really play a very important role. They are given with high priority. Okay. All right. So that is nothing but an interrupt in general. Now, if I have to show you the sources of interrupt, so as I said here, so interrupt can either be internal or external. Okay. So interrupt can either be from the internal devices or the external devices. So the sources of interrupts are either internal or external. Now, if you look at the categories or classification of the interrupt is first divided into two categories. One is hardware interrupt, the other one is software interrupt. If the interrupt is because of some hardware device, it's a hardware interrupt. And if the interrupt is because of some software device, it's a software interrupt. So an example of an hardware interrupt can be an interrupt with respect to the timer, an interrupt with respect to the UART block, an interrupt with respect to the ADC. So any interrupt which has been occurring from any of a hardware, it's a hardware interrupt. Similarly, if the interrupt is because of a software, even the softwares are capable of raising the interrupts. So going ahead in your Linux internals module, you'll come across some of the system calls which literally raises an interrupt. Okay. So if the interrupts are caused from the software, we call it as the software interrupts. So interrupts are mainly classified into hardware interrupts and software interrupts. Now, hardware interrupts are further classified into non-maskable interrupts and maskable interrupts. So, non-maskable means the interrupts which cannot be avoided. Okay, non-maskable interrupts are the ones which cannot be avoided, and maskable interrupts are the ones which can be ignored for some time being. Okay, maskable means it can be ignored. Non-maskable means which cannot be ignored. Non-maskable interrupts should be taken care of immediately, but maskable interrupts can be ignored for some time being. So that's the difference between non-maskable and maskable interrupts. Now, maskable interrupts are further divided into external interrupts and internal interrupts. So external means the one which are caused by external hardware devices. So, okay. So non-maskable means the ones which cannot be ignored. Maskable means the ones which can be ignored. So these maskable interrupts can either be from the external devices to your microcontroller, or it can be from the internal devices which are already available in your microcontroller. So for example, timers will be available in your microcontroller. It's an internal interrupt. So some of the peripherals which are available outside the microcontroller may also raise an interrupt. So for example, RTC. So that's a peripheral which is outside your microcontroller. So that can also raise an interrupt. It's an external interrupt. So maskable interrupts is further divided into external and internal. Yes, keyboard is also working on the basis of interrupts itself. That is why whatever key you are typing, it is given a high priority and displayed immediately on the screen. So every device, like each one of the device will have one or the other sources of interrupts also. Can a device driver be an interrupt? So some of the signals of the device drivers can have the interrupts returned. The whole device driver is nothing but a software. It's a program. So that whole thing you cannot call an interrupt. So there might be certain instructions in the device driver which might raise an interrupt. Okay. So that is nothing but the interrupts engendered. So the classification of the interrupts. So somebody was asking for the previous slide, the sources of interrupt, external interrupt and internal interrupt. So classification, interrupts are first mainly classified into hardware interrupt and software interrupt. Hardware interrupt is further divided into non-maskable and maskable interrupt. Maskable interrupt is further divided into external and internal interrupt. Is this clear? Understood the classification of the interrupts? Okay. What are some of the disadvantages of the interrupt? So interrupts, it is not a big disadvantage as such. Interrupt shouldn't have any disadvantage as such. But if you literally think of the disadvantages of the interrupt, one biggest disadvantage is it can affect the execution of the main code. Okay. So if the interrupt keeps occurring, it can affect the execution of the main code. It's something like when I'm taking the class, if I keep getting the doubts itself, if I keep getting the interrupts itself, either it is internally or externally. So the main intention of our class is to continue with the syllabus. That might get affected. So main task might get affected due to a huge number of interrupts occurrence. That's the only disadvantage which you can consider. Okay. All right. So let's take a break of 2 minutes and then continue with the next interrupt topic. Okay. When multiple interrupts occur, then it would might affect the performance of the system. Is it so? Yes. So that is what I said. That is only one drawback of this interrupt. Okay. Difference between polling and interrupt. Uh, so polling means you are monitoring an event on a continuous manner. Interrupt means you don't have to monitor. The moment interrupt occurs, you will make sure the action is taken for that interrupt. So that's the main difference between polling and interrupt. The action is taken immediately whenever an interrupt occurs, but in case of polling, to take the action, you have to monitor an event on a continuous. Okay. Now going ahead, just assume you are inside your super loop. Super loop means your while of one loop. Okay. So you are here executing your super loop, which is nothing but your while of one loop. Now you keep executing the instruction one after the other. So something like this, every instruction will be taken care of. At the ith instruction, there is an interrupt occurring. Now, when the ith instruction, at the ith instruction, when the interrupt occurs, interrupt will go and handle the interrupt, which is called as interrupt handler. So, whenever an interrupt occurs, so control will go to handle the interrupt, which is nothing but interrupt handler. And after the interrupt is handled, it comes back and resumes the next instruction's execution. That is I plus 1th instruction's execution. So that is how an interrupt is handled. So in your super loop, okay, yes, it's just like a function in fact, but in case of function, you have to call it, but here you don't have to call it. The moment interrupt occurs, by default, it will go take care of the interrupt handler and comes back to execute the I plus 1th instruction. So that is nothing but how an interrupt is actually handled. Now, technically, if you speak, when it comes to the interrupt, okay, please understand, in fact, when ith instruction is being executed and an interrupt occurs, you will not immediately go and handle the instruction. I mean, for example, I'll take one more scenario. So assume it's a lunch time of yours. Okay, you have taken a plate, you have served your food, and you have started eating. Okay, so it's like you have to finish the food. So that is the purpose. So eating and finishing the food is your particular purpose. Now you have taken the food, you have placed the food on your plate, you have taken a bite of the food into your mouth. Okay, assume you have put the food into your mouth. The food is already placed inside your mouth. Okay, you just have to chew it and you have to swallow it. Now you have just started chewing it, and let's say a friend of yours will come and he says he wants to talk to you. Okay, a friend of yours comes and he says he wants to talk to you. There's food already in your mouth. Do you directly start speaking with your friend, or you will finish the food which is in your mouth, at least you swallow and then talk? So what do? Will you talk to your friend immediately keeping your food in the mouth, or you swallow and then talk? So obviously you finish that bite, you swallow it and then talk to your friend, right? Okay. So very similar to that, if your controller has already started executing the ith instruction, so it in fact completes the ith instruction. Okay. It will not pause the ith instruction somewhere in the middle. It will complete the ith instruction. After completing the ith instruction, it will go and handle the interrupt. And after handling the interrupt, it comes back to execute the I plus 1th instruction. So that is how interrupt has been taken care of in case of the uh, microcontrollers. So whenever an interrupt occurs, the ith instruction will be completed. interrupt will be taken care of by the interrupt handler and it continues to execute the I+1 instruction. So that is nothing but the interrupt handler. Now this interrupt handler which I'm talking about, whenever an interrupt occurs, I'm saying interrupt handler will get executed. Now what is this interrupt handler, or how can we be handling a particular interrupt? Okay. Now if you think of the ways of handling a particular interrupt, there are two ways of handling any source of interrupt. Okay. So it depends on which microcontroller you have been dealing with, okay, or which particular handler is available. In any of a given microcontroller, there will be either of the two interrupt handlers available. There will either be a IVT available or there will be an ISR available. Okay. So there is an IVT available, there will be an ISR available. So what do you think IVT stands for? What do you think IVT stands for? Yes. So IVT stands for interrupt vector table. And what do you think ISR stands for? Yes, interrupt service routine. Okay. Now, what is the difference between the two? So, what happens if IVT is the interrupt handler? What happens if ISR is the interrupt handler? Now, in case of IVT, please understand every source of interrupt. Okay. So, every source of interrupt every source of interrupt will have its own separate ISR return. Okay. Every source of interrupt will have its own separate ISR return. Okay. So IVT is the table which holds the address of each ISR. Okay. So IVT is the table which holds the address of the ISR. So for example, let's say there is a source called UART. So UART is one of the source of interrupt. So assume its ISR function is available in the address 0x00. Okay, just an assumption. So the ISR of UART is available in the address 0x00. So I would say ISR of UART. Okay. So it's available in the address 0x00. Then one more source of interrupt, let me take it as timer. Okay. So the ISR of timer, okay, is available in the address 0x, let's say 56. Then one more source of interrupt is ADC. So the ISR associated to the ADC, okay, so is available in the address 0x, let's say 78. The ISRs means they are like the functions which will have the set of instructions returned to be executed when that particular source of interrupt occurs. Okay. So the ISR of UART is in the available 0x00. Timer of the ISR will be ISR of the timer will be available in the address 0x56. ISR of the ADC is available in the address 0x78. What do you mean by every source of interrupt will have its own separate ISR return? So I'm telling, when UART interrupt occurs, what needs to be done is return in an interrupt service routine. It's a function. So when an interrupt occurs with respect to the UART, then I have to execute this function. If interrupt occurs because of timer, I have to execute this function. If interrupt occurs because of ADC, I have to execute this function. So for every source of interrupt, there will be a separate ISR return available in different addresses. Okay. So your interrupt vector table is going to hold the address of each ISR. So a table will be created like this, representing if UART is there, its ISR is available in the address 0x00. If timer interrupt is occurring, its ISR is available in the address 0x56. If ADC interrupt is occurring, its ISR is available in the address 0x76. So IVT will in fact hold the addresses. I'm sorry. So IVT in fact is going to hold the addresses of the ISR of a particular source of interrupt. Now, for example, how the operation happens is, assume you are in the main function. Okay. So assume while you are inside your while of 1. Okay. So there is an interrupt occurring. So assume the interrupt occurs due to the UART. Okay. So assume there is an interrupt due to the UART. So what this does is, it will first go check the interrupt vector table where the ISR of the UART is available. So it is in the address 0x00. So it will go to the address 0x00. So whatever ISR is available in that particular address will get executed. Okay. Then if the interrupt of the timer occurs, it will go check in the interrupt vector table. So ISR of the timer is available in the address 0x56. So it will execute the function available in the address 0x56. So interrupt vector table will have the mapping of the addresses of the individual ISRs with respect to the sources. So that is IVT way of handling the interrupt. Are you following this? Doubt. Can we write a function in the while loop? Obviously, yes, you can have a function return, but that function keeps executing again and again. Like, you can have a function return, it depends on how you do the function call. So only if you do the function call, the function gets executed, no? So it completely depends on how you have returned the function. Can we call the function in while of 1? Obviously, yes. You can call the function, there is no doubt in that. Okay. So an example for the controller which has IVT way of handling the instruction is your 8051 microcontroller. Okay. Your 8051 microcontroller handles the interrupt in the IVT way. Now coming to the ISR way of handling the instruction, there will be only one ISR. There will be only one ISR for every source of interrupt. Okay. So whatever is the source of interrupt, you will have the same ISR called for every source of interrupt. That is ISR way of handling the interrupt. For example, assume you are inside main function. So you are inside your while of 1 function. Okay. And being inside your while of 1 function, so assume there is an interrupt occurred because of UART. So it will go to the ISR. Okay, there is one ISR commonly returned for every source of interrupt. Doesn't matter what is the source of interrupt, every time the same ISR is going to get called. So obviously there has to be some differentiator inside the ISR. So we will see it later. But remember, whether the interrupt is because of the UART or timer or ADC or any source, it keeps calling the same ISR. So that is ISR way of handling the interrupt. So in IVT way of handling the interrupt, every source of interrupt has a separate function return. There was a separate ISR return. Okay. So there was a separate ISR return. Voice is breaking. Okay. Okay, fine. All right. So I was saying, um, whenever an interrupt occurs, so you can either handle it using IVT or ISR, depending upon what is the interrupt handler in the given microcontroller. In case of IVT, every source of interrupt will have an individual ISR return. In case of ISR way of handling the interrupt, for any source of interrupt, you will have the same ISR return. How the hardware interrupt takes care. So it can be any source of interrupt. Okay. So whether it is the software interrupt or the hardware interrupt, whatever is the source of interrupt, so it will be handled using either the ISR way or the IVT way. And the example for the microcontroller which have ISR as the interrupt handler is our own PIC16F 877A microcontroller. So that has ISR way of handling the interrupt. So for every source of interrupt, it goes to the same ISR. Whenever an interrupt occurs, ISR is going to get called by default and you are going to take the action inside the ISR. Understood the two ways of handling the interrupt? Is this clear? Okay. All right. So let us proceed. So this is things talking with respect to the ISR. Okay, so this because our microcontroller has ISR way of handling the instruction. So it is talking about ISR. Now what is ISR? It is similar to a subroutine. Subroutine means a function. So it is similar to that of a function. Now please understand what and all happens when an interrupt occurs and ISR is being called. So because in our case it's the ISR way of handling the interrupt. So whenever an interrupt occurs, so ISR gets called. So what and all happens meanwhile, you please see. So whenever an interrupt occurs, it attends to the request of an interrupting source. Okay. So our microcontroller is going to attend the request of an interrupting source. Now it is speaking about three different things. One is it is going to clear the interrupt flag. So please remember this. It is going to clear the interrupt flag. Should save the register contents that may be affected by the code in the ISR. Must be terminated with the instruction RETFIE. So RETFIE is return from interrupt. Okay, so that is RETFIE. See what happens whenever an interrupt source creates an interrupt. So the first thing your microcontroller does is it is going to clear an interrupt flag. Okay. So I told you for every source of interrupt, I will call the same ISR. Now coming to the same ISR, how to identify whether I came to the ISR because of UART or how to identify if I came to the ISR because of the timer or because of the ADC, we will have something called as interrupt flag. Okay, so we will have something called as the interrupt flag. Looking at this, we can decide what is the source of the interrupt. So the first thing what your controller does is it first clears the interrupt flag. So there will be an interrupt flag which needs to be cleared. Then sometimes what happens is when you are executing the ISR, there might be chances that it may change some of the values of the registers. Okay, so register of port B or tris B or port C, tris C. So whatever registers we are dealing with, there are chances that your ISR might affect the contents of the register. So your microcontroller is actually going to save the contents of the register which may get affected by the ISR. So it is going to keep it as a backup separately. And once the ISR is executed, it is going to come out of the ISR with the help of our function call. So this is an instruction. In fact, it's a system call instruction called as RETFIE, return from interrupt. So due to that instruction, so the control will come out of the ISR and continue to execute the I+1 instruction. Okay. So as I said, what the microprocessing unit does is when an interrupt occurs, it first completes the instruction which is being executed. So ith instruction it completes. Then it is going to disable global interrupt enable. One more bit, please remember, it is going to disable global interrupt enable. Then it is going to place the address from the program counter on the stack. So what is this program counter is? It is just like a register which stores the addresses of the instructions to be executed one after the other. So for example, if you look at this slide, so program counter will have the address of the first instruction, second instruction, third instruction, fourth instruction, ith instruction, I+1 instruction. Every address will be stored in the program counter. Okay. When an interrupt occurs at the ith instruction, okay, so what it does is, it in fact stores the I+1 instruction address from the program counter into a stack frame. So it copies the I+1 instructions address from the program counter and keeps it stored in the stack frame. So that is what your microprocessing unit does whenever an interrupt occurs. So RETFIE means it's an instruction which will bring the control back from an ISR to execute the rest of the instructions. Okay, so that is return from interrupt. So this is what happens whenever an interrupt occurs. I hope you are able to follow. And this slide, in fact, is talking about what to be done and what not to be done in an ISR. What can you be doing and what you cannot do being in an ISR. Now, please understand a very simple thing. You always have to keep the ISR as simple as possible. That is really important. So keeping the ISR as simple as possible is very important. So I would say, so do's and don'ts. Do's and don'ts in ISR. Okay. So first one is keep the ISR very simple. So do not involve multiple complexities inside the ISR. Keep it as simple as possible. Second one, avoid blocking statements. So in fact, I suggest you to avoid it in the main application itself. So even in your ISRs, you should never be using any blocking statements. Okay, it is dangerous because if you get stuck in the ISR, the main application is going to get affected. Okay. Yes, any loops, while loop, for loop, so do while loop, all of them have to be avoided in case of the ISR. So you should always avoid writing the blocking statements. So also take care that ISR is not consuming much time to execute. So consuming much time to execute. Now, why this is really important is, let me give you a simple example. Assume you are inside while of 1. Okay. So you are inside while of 1 and assume there is a timer which is generating the interrupt for every 1 second. The timer, it is generating the interrupt for every 1 second. Okay. Now, whenever an interrupt occurs, where will the control go? In case of our PIC microcontroller, whenever an interrupt occurs, where will the control go? Yes, it goes to the ISR. Now assume ISR is approximately taking 2 seconds for its execution. Okay, so just assume ISR is taking approximately 2 seconds for its execution. But the timer is actually generating the interrupt for every 1 second. Now what happens is, in case of while of 1, when timer generates an interrupt after 1 second, control will go here. It will take 2 seconds to execute the ISR and come back. By the time you come back from the ISR, don't you think timer would have raised another interrupt meanwhile? Somewhere in the between, don't you think the timer has caused another interrupt? Yes. And in case of our microcontroller, in fact, when an interrupt is actually being served, it cannot handle another interrupt. Okay. When an interrupt is actually being served, it cannot handle another interrupt. That's the problem with respect to our microcontroller. Okay. Now what happens is, if your ISR is taking 2 seconds for its execution, there are chances that I might miss the interrupt of for every 1 second. Okay. Every alternative second I will miss an interrupt. So that is possible in case of our microcontroller. So you always have to make sure the interrupt, the ISR is being kept as simple as possible. Okay. So it's really important that you take care of the ISR, what you are writing. It has to be kept as simple as possible. So that is the do's and don'ts of the ISR. So you have to keep the ISR as simple as possible. Okay. You have to keep minimal amount of statements to be executed. You have to avoid writing any blocking statements, and you have to take care that ISR is not consuming much time for its execution. So that is do's and don'ts to be followed in case of ISRs. I hope you are able to follow this. Okay. So moving ahead, the last theoretical topic of interrupts is nothing but latency. Now, in short, if I have to say what exactly is the latency, there's a doubt. 1 second, let me read. So, if it is not able to manage only a single element's execution, how it will manage for others, as it has common address for all? See, I'm not telling it cannot handle one element's execution. So I'm telling, when an interrupt is already happening, when an interrupt is already being taken care of, it cannot handle another interrupt at the same time. Okay. So it is challenging. For example, you are already talking to some person. Okay. It is already an interrupt. You're already talking to a person. One more interrupt occurs at the same time. It is quite challenging to handle. So that is a case of any given microcontroller. But especially in case of our PIC microcontroller, when an interrupt has been handled, you cannot take care of another interrupt. That is why we say keep the ISR as simple as possible. Okay. So if the ISR is kept simple, more time is not consumed. Guys, please take care of your mic. Okay. So when I say ISR has to be kept as simple as possible, so that means it shouldn't affect another source of interrupt to be taken care of. So that's the whole idea. Okay. So here what I said was like an unrealistic example. So timer generating interrupt for every 1 second, ISR taking 2 seconds for its execution. 2 seconds in fact is quite a very large time when it comes to the execution of any instruction. So I'm just telling that you have to keep ISR simple so that none of the interrupts are missed out due to you taking much of your time to execute one single ISR. Okay, fine. So proceeding ahead, interrupt latency is nothing but the time it takes, in short, if I have to say, the time it takes to reach from this place to this place is nothing but interrupt. So the time it takes from the moment interrupt has occurred to the time the first instruction in the interrupt handler is executed is nothing but interrupt latency. Okay, so let me make a note here. So I'm talking about interrupt latency. Okay, it's the time taken to execute the first instruction in the interrupt handler. Okay, so time taken to execute the first instruction in the interrupt handler from the time interrupt has occurred. Okay, so that is nothing but interrupt latency. So the time taken to execute the first instruction in the interrupt handler from the time interrupt has occurred is nothing but interrupt latency. And interrupt latency depends on several factors. So it has been listed here. First one is the instruction time. So how much time it takes for the instruction to get executed. Okay, so that means when ith instruction is being executed, if the interrupt occurs, I have to finish executing the ith instruction. Only then I will go handle the interrupt. So the time it takes to execute the ith instruction matters in case of latency. Then how much context must be saved? So I told you that when an interrupt occurs, there are chances that the ISR might make some changes to the contents of the registers. So I will generally back the contents of the registers before the ISR is being taken care of. So it completely depends on how much amount of data I have to back up. Okay. So when an interrupt has occurred. Then it also depends on how much content must be restored. So there is certain amount of data which needs to be restored for every ISR's execution. So it also depends on how much content needs to be restored whenever an interrupt has to be taken care of. Then the effort to implement the priority scheme. So some of the cases, there will be a high priority instruction to be executed, which is more important than an interrupt. Okay, so that also depends whenever an interrupt has to be taken care of, and time spent executing the protected code. So there will be some protected code also to be executed whenever an interrupt is occurring. So all of this matters for the latency. Okay, so that is nothing but interrupt latency. And this is about the theory of interrupts. Any doubt? Is any doubt up to this? When multiple interrupt occurs, which can be executed first? So whichever whichever gets occurred first. So there will be a difference, a slightest difference in few picoseconds or nanoseconds. So whichever interrupt has occurred first will be taken care of. And how it affects the data in the register, can you explain? You will see going ahead. Being in the ISR, there are chances that it might affect the data of some registers, not just your port B or tris registers. So it's like you will see ahead there is something called as shift register, buffer register, which you come across later. So those registers can get affected due to the instructions execution in the ISR. So that is why we generally back it up before the ISR has been handled. Isn't there an interrupt priority table? So generally it is maintained, but as I said, whichever interrupt occurs first, your controller will go to handle that particular interrupt. Yes, so I can say first in, first out. Okay. So scheme of the interrupts also varies from one controller to another, but generally it is first in, first out all the time. Any doubts in the theoretical part of interrupts? The next we have to start with is programming an interrupt. Okay, so we have to start by configuring one interrupt, and in fact with that programming part I can also show you how to overcome the drawbacks of polling using the interrupt. All of these drawbacks, the bad response time, loss of event, inefficient power management, all of this can be overcome with the help of interrupts. So if I use interrupts, I will always have good response time. If I use interrupts, it is very less that I am going to lose any event unless you have written a very big ISR. So it is generally a very rare scenario that I lose any of an event. And using interrupt, I obviously can manage the power on a very efficient manner. So in tomorrow's class, we will see how to overcome the drawbacks of polling with the help of interrupt. So we have to start with the configuration of the interrupts in the next class. But as I said, I'm going to configure the interrupts. I want to know certain things with respect to the interrupts of our microcontroller. So I want to know things with respect to the interrupts of our microcontroller. Which document do you think I should be referring for that? Which document should we be referring? Yes. So we have to go look at the data sheet. Now let me take you to the data sheet. I will just highlight things and then the rest of the things we can do it later also. I will first take you to the table of contents. Please look at the table of contents and then decide which section should I be referring to know things with respect to the interrupts in our microcontroller. Which section do you think I have to be referring in order to do the configuration of the interrupts? Is there any section which is telling a word called interrupt? Is there any section specifying interrupts as such? Section 14.0, is there any section? Okay, 10.0 is, it is talking about user. Section 16 is development support. Okay, all right. So section 15, in fact, the special features of the CPU is the one which is talking about the interrupts in short. So this section 14, if you expand, I have multiple subtopics here. And the one which we have to refer is section 14.11, which is talking about interrupts. Now, I just want you to read certain things. I mean, only this one part. Can you please read these 4 lines and let me know once you are done? And also, I think you can read this also. So this line also. Okay. So how many sources of interrupt does our microcontroller have? The PIC16 F877A microcontroller has 15 sources of interrupt. Okay. Now, if you look at this, please understand for every source of interrupt, it is talking about two bits. One is individual interrupt flag bit, the other one is individual interrupt enable bit and global interrupt enable bit. So I'll write it down here. So first one is individual interrupt flag bit. Okay. Then individual interrupt enable bit. Okay. And the last one is global interrupt enable bit. Okay. Now what are these bits? See, I told you for any source of interrupt in case of our microcontroller, where will the control go? Whatever is the source of interrupt, where will the control go? If the interrupt is occurring, so control will go to the ISR. Now, how to differentiate if I came to the ISR because of a particular source? So that is with the help of individual interrupt flag bit. So these 15 sources will have their own individual interrupt flag bit. Okay. Every single source will have its own flag bit, that is individual interrupt flag bit. So this will be set by the microcontroller whenever an interrupt occurs. Set by the microcontroller when the corresponding interrupt occurs. Okay, so that is nothing but individual interrupt flag bit. Every single source will have its own flag bit, which will be set by the microcontroller when the corresponding interrupt occurs. Similarly, every single source will have its own enable bit. Okay, so will have its own enable bit. Okay, and this will be set by the user. Okay, set by the programmer when the corresponding interrupt should be enabled. Okay, so this will be set by the programmer when the corresponding interrupt should be enabled. So that is individual interrupt enable bit. And the last one is global interrupt enable bit. So if GIE, global interrupt enable, is returned with the value 1, all 15 sources are enabled. Okay. Similarly, if GIE is returned with the value 0, all 15 sources will be disabled. So I think more about this we will discuss again tomorrow. Okay, I'm just making a note of it. Okay, so 15 sources of interrupt are available for our microcontroller. All 15 sources will have individual interrupt flag bit, individual interrupt enable bit. Flag bit will be set by the microcontroller. Enable bit will be set by the programmer. Global interrupt enable bit is something which is used by the programmer to enable all 15 sources at once or to disable all 15 sources at once. So more about this interrupt we will see tomorrow, and we will also see how to configure a source of interrupt in tomorrow's class. I hope the class is all been clear. Okay, so give me a second. Please have your attendance marked before quitting. Okay. So here is your QR. Please have your attendance marked and then quit the session. Thanks for attending today's class. We will continue tomorrow. Thank you all.